Sometime later this year, an instrument that has been running continuously since 1977 is going to go dark forever. And when it does, it will take with it the primary tool humanity has used to measure exactly how much deadly radiation is actually streaming through the galaxy around us. It's called the Cosmic Ray Subsystem, and for nearly 49 years, it has been quietly building one of the most important safety datasets our species has ever collected, information that directly shapes how engineers think about protecting future astronauts on any mission that dares to travel beyond the safety of our own solar system. This is the real story of what Voyager 2's cosmic ray instrument has actually been telling us, why NASA is about to shut it down for good, and why the warning buried inside its data matters for anyone who ever hopes to see humans travel deep into space. Let's start with what this instrument actually does, because it's easy to hear the phrase cosmic ray subsystem and assume it's some kind of abstract, purely academic tool with no real-world relevance. It isn't. Cosmic rays are extremely high-energy particles, mostly protons and atomic nuclei, accelerated to tremendous speeds by some of the most violent events in the universe: exploding stars, the aftermath of supernovae, and other extreme astrophysical processes happening light years away from anything we could ever hope to survive up close. These particles are energetic enough to punch straight through solid matter, and when they pass through living tissue, they can damage DNA at the cellular level, contributing to increased cancer risk and other long-term health consequences. Here on Earth, we're protected from almost all of this radiation by two overlapping shields, our planet's own magnetic field, and at a much larger scale, the Sun's heliosphere, the enormous bubble of solar wind and magnetic field that envelops our entire solar system. Voyager 1 and Voyager 2 are the only two instruments humanity has ever placed on the outside of that second, larger shield, giving scientists their only direct, real measurements of what cosmic radiation levels actually look like once you leave the heliosphere's protection behind entirely. Voyager 2's specific cosmic ray subsystem consists of 3 separate telescopes, instruments specifically engineered to measure the energy and flow, or flux, of cosmic ray particles, whether they originate from our own sun or from the distant reaches of the galaxy. This isn't a new or recently installed piece of equipment. It's the exact same hardware that launched aboard the spacecraft back in August of 1977, built using the engineering standards and materials available nearly 5 decades ago. And it has been operating essentially continuously since that launch, through flybys of Jupiter, Saturn, Uranus, and Neptune, and through the spacecraft's historic crossing into true interstellar space in November of 2018. That continuous operation is exactly what makes the data this instrument has collected so genuinely valuable and so difficult to replace. When Voyager 1's identical cosmic ray subsystem was still active, its measurements played a direct critical role in helping scientists pinpoint exactly when and where that spacecraft actually crossed the heliopause, the true boundary of our solar system, back in 2012. The instrument detected a sharp, unmistakable shift in the balance between solar cosmic rays, particles originating from our own sun, and galactic cosmic rays, particles originating from far outside our solar system entirely. Inside the heliosphere, solar particles dominate. Outside it, galactic particles take over almost completely, and that shift, captured directly by the cosmic ray subsystem, became one of the clearest, most reliable signatures scientists have for confirming exactly when a spacecraft has genuinely left the sun's protective influence behind. Here's the part of this story that carries real, practical weight beyond pure scientific curiosity. The heliosphere, as Voyager 1's own data helped confirm, blocks more than 70% of incoming galactic cosmic radiation from ever reaching the inner solar system, including Earth itself. That's an enormous, genuinely life-preserving amount of shielding, quietly protecting every living thing on this planet for the entire history of life on Earth, largely without any of us ever having to think about it. But that same protection simply doesn't exist once you travel far enough away from home, and understanding exactly how much radiation exists on the other side of that shield, in real, measured, direct terms, rather than theoretical estimation, is precisely the kind of information that mission planners need if humanity is ever going to seriously consider sending astronauts on journeys that push meaningfully beyond our own solar system's protective bubble. Voyager 2's cosmic ray subsystem has spent years gathering exactly that kind of direct, irreplaceable measurement, data confirming that cosmic ray levels beyond the heliosphere are dramatically higher than anything found closer to home, exactly the kind of real, hard number engineers need when calculating how much shielding a future spacecraft, or a future astronaut's suit, would actually require to survive extended exposure to that environment. This isn't abstract information filed away in an academic journal nobody outside the field will ever read. It's a direct, practical warning about the genuine radiation risk waiting beyond our solar system's natural protection, quantified using real measurements rather than theoretical models alone. And now, that specific instrument's nearly 49-year run is coming to an end. NASA has confirmed that Voyager 2's cosmic ray subsystem is scheduled to be shut down later this year, part of the same careful, deliberate power conservation strategy that has already claimed several of the spacecraft's other original instruments. The math behind this decision is unforgiving and entirely outside anyone's control. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity, and that power output has been shrinking by about 4 watts every single year since launch, a slow physical decline nobody can pause or reverse. Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, explained the stakes in blunt, practical terms, saying that if engineers didn't turn off an instrument on each spacecraft when they did, both Voyagers would likely have had only a few more months of power left before the entire mission would need to be declared over. This shutdown is part of a longer, carefully sequenced pattern of losses that has been unfolding in real time over the past 2 years. Voyager 2's plasma science instrument was switched off in late September of 2024. Voyager 1's own cosmic ray subsystem was shut down in February of 2025. Voyager 2's low-energy charged particle instrument followed in March of 2025, and Voyager 1's equivalent instrument was shut down more recently still, in April of this year. Once Voyager 2's cosmic ray subsystem goes dark later this year, both spacecraft will be left with exactly 2 functioning instruments apiece. The same 2 on each, a magnetometer measuring the surrounding magnetic field, and a plasma wave subsystem measuring the density of interstellar plasma. Those 2 instruments were deliberately chosen to be the last ones standing, because together they return the science most specific to interstellar space itself. Information that no other instrument on any other spacecraft anywhere is currently capable of gathering. Voyager project scientist Linda Spilker captured the emotional weight of this entire ongoing process with a line that has genuinely stuck with a lot of people who've heard it. Every minute of every day, she said, the Voyagers explore a region where no spacecraft has gone before, which also means every day could be their last. But she added something equally important. That same day, she said, could also bring another interstellar revelation. A reminder that even as this mission steadily loses pieces of itself, what remains is still actively, genuinely capable of teaching us something new. There's a specific engineering detail buried inside the shutdown of Voyager 2's cosmic ray subsystem worth appreciating, because it says something about the sheer, quiet durability of hardware built nearly 50 years ago. The instrument, like several others aboard the spacecraft, relies on components that were never expected to still be functioning at this point. Voyager's low-energy charged particle instrument, a close relative of the cosmic ray subsystem, includes a rotating platform powered by a small stepper motor, originally tested on Earth to reliably survive 500,000 steps, just enough to guarantee it would keep functioning through Voyager 2's flyby of Saturn back in August of 1980. By the time that particular instrument was finally powered down in March of 2025, its motor had completed more than 8.5 million steps, roughly 17 times beyond its original design specification, quietly rotating through the vacuum of interstellar space for over 4 decades longer than anyone building it ever expected it would need to. So here's what I actually want you to take away from all of this. Voyager 2's cosmic ray subsystem isn't just an old piece of hardware quietly being switched off to save a little electricity. For nearly 49 years, it has been directly measuring one of the most genuinely important, practical questions our species can ask about its own future in space: exactly how dangerous the radiation environment becomes once you leave the protective bubble surrounding our solar system behind. That data has already helped confirm the true, direct scale of the shielding our own heliosphere provides, and it stands as one of the only real, measured data points humanity has for understanding what any future deep space mission would actually have to survive. When this instrument finally goes silent later this year, we won't lose the data it's already collected. That record is permanent, and scientists will keep studying it for years to come. But we will lose our only active, ongoing source of exactly this kind of direct, real-time measurement from exactly this region of space for the foreseeable future, until some future mission, decades from now at the earliest, finally manages to reach the same boundary again. If you want to know exactly when Voyager 2's cosmic ray subsystem sends back its final readings, subscribe and turn on notifications, because that shutdown is coming later this year, and we'll be covering it the moment it happens. And drop a comment telling me whether you think humanity will actually launch a proper interstellar mission before either Voyager spacecraft finally goes fully silent. Because right now, the honest answer is that we're not even close, and these 2 aging machines remain the only real window we have into exactly what any future mission would actually be flying into.